The next presenters are Steve Yokum and Michael Durst, talk entitled Creation of a Translator from PLC Ladder Logic to C for the NASA KSC Exploration Ground System. All right, Steve and Michael.
Thank you. Good afternoon. So I'm Steve Yokum and Michael Durst is here. We're from the NASA Independent Verification and Validation Facility. Next slide, please. So for those of you who don't know, NASA IV&V is we're an agency-wide service that provides a high level of safety and mission for the NASA's highest mission-critical systems. That's usually the planetary explorers, the Mars rovers, telescopes, and of course anything that's man-rated has to go through the IV&V Center. Most of what we do there is static analysis of software requirements, designs, things like that. But in addition to that, team that I'm on is the independent test capability. We actually build dynamic simulations of these missions, but they're all software. We don't use any of the hardware components that are in the vehicle. We do this through virtual machines and porting and things like that to get to where these simulations can run typically on a laptop computer. Some of the ones we've done in the past are the James Webb Space Telescope, SLS. I'll be talking about components of that today. That's the new launch vehicle. And then Europa Clipper is one we're working on right now. And that's one of the planetary explorers. Next slide. So the simulation, one of the bigger simulations we're building up right now is this one called Aristotle. It's an acronym. I'm not going to try to define what that is, but that's an all software simulation of SLS, the Orion vehicle that sits on top of there that'll take the crew, I think ultimately to the moon, maybe beyond as this expands. And then KSC, which is the launch facility where they do all the buildup, the tanking, the countdown to actually launch the vehicle. SLS, these are all virtual machines that we've integrated together over a virtual scramnet bus that we've built as well. SLS starts with Marshall's Artemis simulation. We've added on our own flight computer models so we can run the binary unmodified. Orion uses Socrates. That pretty much comes unmodified from Lockheed Martin. And then KSC software is an AIX-based system that runs on Linux. We've had to port that to Linux to run in our framework. And then all this runs at something other than real time. So those are all issues we've had to tackle to get all this to run on one single commodity piece of hardware, commodity piece of hardware, being a high-end laptop, without using any hardware. So as long as you have 128 gigs of RAM, which is quite a bit, you can run this entire system in our all software simulation. Next slide. One of the big challenges we hit with this simulation, though, was that Kennedy uses a whole bunch of PLCs to control their systems. So the cryogenic tanking, the launch release system that holds the vehicle in place prior to launching, the countdown clock you're very familiar with in the press, the water suppression system, those are all PLC controlled. So to close the loop on this simulation, we really have to bring this logic into our all software simulation. But the PLCs present a problem here, and that's they're written in a language that there's no interpreter for it. There's no way to compile it. There's no way to run it on Linux per se, or any other commodity piece of hardware. You can only run it on the PLC hardware. So kind of got a snag there. So we had to figure out how we bring in that logic to the bigger Aristotle simulation. Next slide. One of the solutions that was out there was this product called Softlogix that Rockwell Automation is who builds the PLC hardware. They have this product called Softlogix, which would run the PLC in a virtual environment, but it had a lot of limitations that kind of we couldn't overcome. One is that it ran in a Windows platform. We're kind of Linux based. We don't run real time. This was constrained to real time. And probably the biggest showstopper is this has now gone end of life. So it's not going to be supported or sold anymore in the future anyway. So everyone has to move off of this solution if they're currently using it. So this turned out to be not an option for the ITC team at IVNV. Next slide. So what did we do? We decided, well, maybe we can take this ladder logic, and Michael will get into more of what that actually means here in the future slides. But maybe we can take this logic and translate it into some other language that we can actually run. So when we started looking into that, we found that what's saved when you write your ladder logic code all gets stored into an XML format called L5X. So what we did and what we're going to discuss here is we used Python, which is a very good language to read XML, a very good language to parse text, and we translated that L5X XML that represents the PLC language to the C language. Obviously, once you get in C, a lot of those barriers come down. Now we can compile for essentially any platform. We can apply wrappers to this to do the timing. The ladder steps, they happen in certain sequences. So we added the wrappers to do the timing, to do the interfaces to other systems, and that's how we were able to integrate and run the PLC logic in our larger sim. Next slide. Okay, so I'll turn it over to Michael now, and he's going to go into more of the details about how we got this translation.
Hi, I am Michael Durst. So initially there are 5 languages that are supported by Rockwell PLCs: RLL, Relay Ladder Logic, Functional Block Diagram, FBD, Structured Text, Instruction List, and Sequential Function Chart. So at Kennedy, only 3 languages are supported. So our system, our encoder system, only supports those 3 languages, which are FBD, RLL, and ST. Next slide. Oh yeah, quick disclaimer on all code examples. None of it is ITAR. It is all just completely fake code examples generated from faked out L5Xs. So the first step in generating this PLC code to C was creating a map of types. So for example, you can see here, you've got your base types on the left, which are things that we put into a header file to have simple one-on-one matchups to the PLC types to a similar, well, an identical C type. Then there are auto-generated types, as you can see on the right-hand side, which come from the configuration file from the L5X itself as it's defined, and the Python parses that and then converts it into its equivalent C. Next slide. So the first and probably most important language that we set out to tackle was RLL. So it's a graphical-based language that it was originally made to be similar to relay diagrams to help ease electrical engineers into the coding world with something that they were kind of familiar with. So the way it works is it's a set of functions that run left to right, top to bottom on rungs. And they take different actions depending on the power state coming into the function. So if you take a look at our example to the left here, you have a timer, which if it is done, will turn a switch on or off, allowing power to move through this function. And how the blocks afterwards, like the add, move, and PID, react will depend entirely on the state of that timer. So essentially, lost it. The next slide, please. So here's an example of the translated code. Initially on the far left side, you can see what it looks like graphically. In the center, you can see what it looks like in the L5X, and then the equivalent C code is there at the bottom. Essentially, we run a run condition, which is essentially a Boolean array. And whenever you have the initial state, which would be the enable in, which is true, comes in, it is then separated amongst the two run conditions. And then we run the logic for the top first, and then the logic for the bottom second. And then those two logic states are actually ORed back together. So anything after that, so say the top half had a power positive state and the bottom half had a power negative state, anything after that would still have a power positive state because one of the rungs was in fact positive. Next slide, please. Okay, so the second language that we chose to work with was FBD. FBD is very similar to Simulink for anyone that's used that. It's function blocks with data moving across signal wires. It was actually the simplest of the languages for us to translate. The C equivalent operates on structs representing all inputs and outputs of the function blocks. And our converter essentially takes a topological sort to maintain the order between the inputs and outputs. So there are wires connecting each functional block, and by knowing what is an input and output, we then sort. So it gives a semi-random order, but the logic is always in the correct order. And if you look there at the bottom left side, there's an example of the logic of an FBD function, not the auto-generated code. Next slide. So here's an example of an FBD conversion. Here, it's a little hard to look at since, like I said, it does a topological sort, but the left-hand side is what FBD looks like graphically, and then on the right-hand side is the auto-converted C. Next slide. Next slide, please. Okay. And then the third and final language that we converted was ST. It's more complex syntax than FBD and RLL, since it's not just a basic L5X, or it's just not just a basic XML structure. There actually had to be some parsing involved with this. It reuses any functions that are found in ST are either from FBD or RLL. So all that is code reuse. And then all the statements have to be tokenized and then translated to the equivalent C. So as you can see here on the left, that is an example of ST within the Rockwell L5Xs. Next slide. So as you can see here, here's an example of the ST to the left and the equivalent C on the right as it's translated. So while there are a few minor things that are a little different, it's essentially just identifying tokens and then creating the proper and then translating it to C. Okay. Next slide. So essentially our PLCs have three main threads of execution in which upon initiation, they start up an ESDK callback loop, which is for comms between them and other simulations and also gateways. Then there is a logic loop which runs continuously, and then there's another comms loop meant for messaging. And then all are rejoined together at shutdown. Next slide. So once the PLCs are started up, they run through essentially a continuous cycle until shutdown and continuously scan over their logic. where the inputs update, you run through the functions, be they FBD, RLL, or ST, based on task timing and scheduling and all that, whatever the task at hand is. Then they update the outputs, and then it just starts all over again until it is shut down or put into sleep mode. So all of our telemetry inputs and outputs are handled via ESDK, a CODIS SIP networking library. Okay, next slide. And this is the overall diagram for how our PLCs set into the KSC simulation that we do at IVNV. So essentially, we take these L5X catalogs, convert them into C using our conversion tool, compile and link, and then try to put our PLCs in between our own gateway software and trick simulations that are government off the shelf from KSC. Next slide. So for now, we run with 52 KSC simulated PLCs. The maximum number that run on any of the sim catalogs that we work with is 42, and it's approximately 197,457 lines of auto-generated code, not including hand-generated functions. Are there any questions?
One more slide.
Oh, next slide. Sorry.
So now that we have this functionality added into Aristotle, the SLS simulation, this gives the IVNV analysts the ability to now execute a whole new suite of tests on the ground that was no longer possible. Plus, it allows the loop to be fully closed with things like cryogenic tanking and launch release and those type of operations. So in addition, this is all part of the bigger Artemis program. This is the push to get man back to the moon. So we foresee this being used for many years to come. KSC is obviously going to remain as NASA's primary launch facility. So we'll be doing verification on this with many future missions as NASA continues with the SLS and Orion programs. So that concludes our presentation. Any questions?
Yes, it looks like we have two questions in the question and answer. The first one from Leonidas Cosmidas is, do you run any equivalence checking tool between the original languages and the final generated code, or is it not required since the software is not actually flying but mostly focused on testing?
So yes, we did actually create several tests where we would use Softlogix, which is the old system, to essentially we would run a test and give inputs to it and then log all the outputs, and then would compare the same test on the auto-generated code to make sure they matched up. But it's not a super high level testing.
Okay. And one other question came in, but next question is from Alec Waterlow. Were any specific Python libraries used for the XML to C conversion?
Yeah, we used LXML.
Okay. Next question is from Mark Wu. What model Rockwell PLC is being used by KSC? Your examples show AOIs, which suggest control logics or guard logics, but then your example indicated synchronous IO updates, which is not the case for those platforms. Is Ethernet IP-based IO? Is it Ethernet IP-based IO?
Yes, it is Ethernet-based IP-based IO. And I do believe it is Control-Logix.
Okay. Next question related from Ron Marrero. Will this eventually phase out Softlogix use at KSC for launch training?
KSC is taking another approach to this problem. I believe they're doing a hybrid with PLCs, real PLC hardware and a software approach hybrid. I don't know exactly what the details of that are, but they will have to get away from Softlogix, yes.
Okay. And another question from Simon Singh. How does C program maintain the timings maintained by the PLC? How does the C program maintain the timing that is in the PLC?
So it's just a simple auto-generated scheduler that pulls all these timings out of the L5X configurations, and then the scheduler runs the timings as they are configured.
Mm-hmm. Okay.
Also, this doesn't run at real time most of the times.
Yeah, so and to expand on that question too, everything we run is in sim time, not in real time. So the components commanding the PLC and the simulated components that are being acted upon by the PLC are all running under a common time step, which is our simulation time. So we don't have to maintain a hard PLC ladder step. I don't know what the right term is, but because everything runs within a simulation step, if that makes sense.
Mm-hmm. Okay, great. We may have answered all the questions. If we have a couple more minutes, if people want to jump in there with a few more questions, we'll give that a minute or two. And if not, next up is a break. All right, and other questions can be, some of these conversations can be taken over to Slack, and you can follow up with any questions you have.